Hello, I'm the mobile Mr. Daycock, and today I'm going to be teaching you about de Moivre's theorem. Now, de Moivre's theorem is a theory in complex analysis that allows you to deal with things like this a lot more easily. It also has a lot more power than that, and we'll go more into that in the next video. But right now, we're just going to look at de Moivre's theorem and look at how it helps us with calculations like this. So de Moivre's theorem tells us one simple thing: if you have cosine theta plus I sine theta all to the power of n, then that is exactly the same thing as cosine of n theta plus I sine of n theta. Now, that might seem like a surprise, but actually it's really easy to prove with Euler's formula, or Euler's relation. Let's get that right. Because all we have to do is say that cosine theta plus I sine theta to the n, well, our Euler's relation tells us that cosine theta plus I sine theta, this bit in here, is just e to the I theta, all to the power of n. And then power laws tell us that that is just e to the I n theta. Now, be very careful. This is only valid for n as an integer. If n is not an integer, if n is some other number such as a half or something like that, it goes wrong because the power of a half is equivalent of a root. And when you take roots, there is more than one possibility. So this only works when n is an integer. Okay, and this therefore tells us that we have cosine, let's go back to the blue here, we've got cosine, there we go, got the blue, cosine of n theta plus I sine of n theta, just by using Euler's relation again. Okay, so that's your proof that it works. And if we were to deal with, say, r to the n times by cosine, so r cosine theta plus I sine theta all to the n, so i.e. that we were dealing with something that didn't just have a size of 1, a magnitude of 1, we had a magnitude of r. Well, fortunately, r is going to always be positive, and so that's going to be just r to the n times by cosine n theta plus I sine n theta. Because we just applied de Moivre's theorem to this part and r to the n on that part. So that works out really nicely. Okay, so let's see how we're going to use that for this issue here. So we've got 3 plus 3i to the power of 5. The power is our 5, so what we want to do is about this bit in here. So we're going to look at r is equal to the modulus of 3 plus 3i, because we need to know the r. That's going to be equal to the square root of 3 squared plus 3 squared, which is equal to the square root of 18, which is 3 root 2. And we need to know theta, which is the argument of 3 plus 3i, which is going to be equal to arc tan of 3 over 3, which is pi over 4. And now we can write it out in our form of r cosine theta plus I sine theta. And so when we're dealing with 3 plus 3i to the power of 5, that is equal to 3 root 2 multiplied by cosine of pi over 4 plus I sine of pi over 4, and all of that raised to the power of 5, which by de Moivre's theorem is going to be equal to 3 root 2 to the power of 5. Well, this is actually just expanding at this point, but we'll get to de Moivre's theorem in a moment, multiplied by cosine of pi over 4 plus I sine pi over 4, or to the power of 5. And 3 root 2 to the power of 5 is going to work out as 243 multiplied by the square root of 32. And by de Moivre's theorem, this bit works out as cosine times by 5 pi over 4 plus I sine 5 pi over 4. And this is de Moivre's theorem. Notice how that 5 came from the power and went into the cosine and sine as a multiple. That is de Moivre's theorem in a nutshell. And now we can work out these. Cosine of 5 pi over 4 in your calculator is just going to work out as negative 1 over root 2. Sine of 5 pi over 4 is going to work out as exactly the same thing, negative 1 over root 2. And we can just plug that in and we get 243. The square root of 32 is actually 4 root 2. So we can get that nicely. Multiplied by minus 1 over root 2 plus, in fact, let's go with minus because it is minus I 1 over root 2. And these root 2's here are going to cancel. And that just leaves us, and 243 times 4 is 972. And so our answer is going to work out as negative 972 minus 972i. Now that seemed quite long-winded. Perhaps you would have a faster way. Once you get good at this, you can potentially skip some steps and get to the answer much, much faster than any other way. Right, let's have a go at this next one. Calculate root 3 plus I to the power of 7. So again, we need to know what r is. R is equal to the square root of root 3 squared plus 1 squared, which is square root of 4, which hopefully we can see is 2. We need to know theta, which is the argument of root 3 plus I, which is arc tan of 1 over root 3, which equals pi over 6. And now, write it as de Moivre's. Using de Moivre's theorem, we are doing 2 times by cosine of pi over 6 plus I sine of pi over 6, all raised to the power of 7. That's what we want to work out. And that is, of course, going to be equal to 2 to the power of 7 times by cosine, let's put that in blue, cosine of 7 pi over 6 plus I sine of 7 pi over 6. That 7 is coming down into our sine and cosine. And now we can work these out exactly the same, just calculating cosine of 7 pi over 6 and sine of 7 pi over 6. Here the 2 becomes 128. Cosine of 7 pi over 6 is minus root 3 over 2. You can use a calculator for that, or whatever method you like. Sine of 7 pi over 6 is minus a half. And then, of course, we've still got the I. And then expanding that, we get 128 divided by 2 is 64. So we get minus 64 root 3 minus 64i. And we're done. Last example before I finish. Calculate 1 plus I to the power of 8. So r is equal to the square root of 1 plus 1, which is the square root of 2. Theta is equal to arc tan of 1 over 1, which is equal to pi over 4. And so what we're doing is we're doing root 2 multiplied by cosine of pi over 4 plus I sine of pi over 4, all raised to the power of 8. And by de Moivre's theorem, that's going to give us root 2 to the power of 8 multiplied by cosine of 8 pi over 4 plus I sine of 8 pi over 4. And that is the same as root 2 to the power of 8. Well, that's the same as 2 to the power of 4. multiplied by cosine of 2 pi plus I sine of 2 pi. But 2 pi is just a full rotation, so that's in fact cosine is the same as cosine of 0 and sine of 0. So this is 2 to the power of 4 is 16. So we've got 16 multiplied by cosine of 0 plus I sine of 0, because 2 pi is a full rotation, which gives us 16 multiplied by 1, cosine of 0 is 1, plus I times 0. And the imaginary part is being multiplied by 0, so it just disappears, and our answer is just 16. So the answer to this one up here, 1 plus I to the power of 8, is just 16. Just a real, whole, completely, no complex numbers whatsoever involved, 16. Okay, and that's the Moivre's theorem, and a simple application of it. We'll go a lot further and produce some very interesting results in the next video. Thank you very much for watching, and I'll see you in the next video.